talk from quantum crystals. So Taylor, take it away.
Thanks. Yeah, it's a real honor to have this talk today. So I'm a chemist theorist from the University of Illinois at Champaign, and I'm one of the coordinators for the Quantum Universe in the Crystal program. That topic is very grandiose and broad. I've chosen to focus on kind of a self-contained story that's going to include some of the themes that we're focusing on. And the topic I'm going to discuss today is about chirality. Now, chirality can have a lot of different meanings. I'm going to define precisely what I mean in a moment about chirality. And the first part of my talk is going to be talking about getting chirality in crystals despite being in a crystal. And the second part of my talk is going to talk about some kind of chirality that appears because we're in a crystal. Right? So when I talk about chirality, I'm really going to talk, have most of the talk talking about one-dimensional chiral modes. And what I mean by that is any type of wave phenomena that has a dispersion relation that's linear in K. This could be electrons, it could be bosons, it could be light, it could be sound, it could be mechanical energy, anything with this type of dispersion relation. So this type of wave phenomena has a group velocity for wave packets, right, the derivative of the energy with respect to position, which is a constant, v. And the chirality of this one-dimensional mode, chi, is defined to be the sign of that velocity. So if it's positive, I have a mode that goes to the right. If it's negative, I have a mode that goes to the left. And we can kind of draw this dispersion relation here, so we have on the board E versus K, and I just have a line. Now I'm going to think about finite systems, so I'm going to think about a finite system, so this one-dimensional chiral mode on a ring, perhaps with periodic boundary conditions, and so the modes are discretized into different momenta. And for example, if this type of modes represents electrons in some material, which it will in most of the cases I'm considering, then these modes are filled up to some chemical potential at zero temperature, and so some set of them are filled, and some set of them are empty. Okay? And so in this picture, I'm thinking about this mode here. Since it has a positive velocity, the chi is +1, and this is a quote-unquote right loop. So what that means is that this mode is like a one-way channel, a one-way street to carry things, whether that is charge, energy, sound, light, whatever we have in this case. Okay? Now I purposely haven't sort of specified a system yet because I said the phenomena I'm talking about go beyond just thinking about electrons and solids. It talks about any type of wave phenomena, right? So in fact, these type of modes have practical applications. This is some practical application that are already in use. Okay? So one place you see these type of non-reciprocal chiral modes is in electronic circuit networks, where you develop what's called an isolator. So you have something here. On the left is your precious network. On the right is the outside world, and you're trying to isolate your network from the outside world. And so you might want to be able to get things out of the network, but not accept noise and all kinds of junk coming in the other side in this case. Okay? So circuit isolators are built on the phenomena of chirality. You can also have things like cloaks, basically cloaking devices. So if you can do this with light, what can happen is you can have some cloak, and you can let light in from one side, so you can see what's on the out, but your light from your body doesn't go the other way, it gets blocked. Right? So cloaking devices are a non-reciprocal behavior built on the idea of some one-way transmission in this case. Okay? You can also get, in solid systems, robust transport. So what do I mean by transport? So this is transport of charge, transport of light, transport of sound, things like that. And the reason you get robust transport is if I have some channel, a wire, for example, or some channel, and it has defects, then since the mode only has one direction it can go, it will simply find a way to make it through this channel. And so you can get this robust transport even in the presence of defects. And this is the place where many type of engineering applications really want to utilize the idea of these chiral modes because they can sort of avoid impurities in this case, and they're very robust. They won't get scattered backward in this case. Right? So in addition to having these kind of useful behaviors, they also have some strange behavior. So what happens, for example, if you try to completely block this, right? I cut the wire, or I make some giant blockade there in this case, right? So you can think about this as solving some kind of barrier problem with a wave phenomenon, right? So I have some barrier here, I've got some mode coming in, right? And the point is that there's no modes going the other way. So the mode here, the chiral mode, just plows right through the barrier. Goes right through. It can pick up a phase shift, but it goes right through because there's no states going the opposite direction. So I can't construct any standing waves or anything like that, and that will go through. In fact, it's even worse than that. I can take this potential basically to infinity, and it will still go through. So this mode is unstoppable in some sense, right? Which is unphysical, and we're going to see how to fix that in a minute, right? So effectively, it can go through any barrier. The second thing you find is that if you start, let's suppose this mode is now a mode of electrons in some wire, and they're filled up with some chemical potential, I can now imagine applying some electric field to get a current in the wire, right? Trying to accelerate the electrons, right? So I'm thinking about my wire, let's say it's being some ring, and now I want to apply an electric field. Right? I still want to use this picture in sort of K-space, and so I don't want to break translation symmetry, so I'm going to apply an electric field through the Faraday effect, right? Faraday's law. So I'm going to turn on some time-dependent magnetic flux, phi of t, and that's going to generate some electric field. Whoops. Circulating electric field in this case, some EX, for example. So by turning on this field, my electric field EX in this setup is going to be the time derivative of my vector potential. And from the way that the momenta couples to the vector potential, I'm going to get the momenta are going to be shifted by this vector potential in this case. Right? So as I accelerate the electrons, what's going to happen is that their momenta are effectively going to rigidly shift as a function of time. Right? I'm going to get some shift in this case. It's a function of time. And if I wait a certain amount of time, the modes are all going to shift by sort of 1 unit, so it doesn't really matter, but the modes are going to trail up like this, and so whoops, keep going up. And eventually, if I wait long enough, I'll have some extra thing which wasn't there before, something which is above the chemical potential, right? An extra charge above the chemical potential. Okay? And so this type of behavior looks on the surface like charge non-conservation. Because I had some fixed system here, and I accelerated electrons, and all of a sudden I've got an extra charge as a function of time. And both of these problems stem from the same issue, which is that we don't actually know what's happening at energy equals minus infinity. The fact that the spectrum is unbounded is really the problem. All the physics that teach you how to treat these chiral modes depends on what's happening there. And depending on what context I'm in, whether it's high energy physics, whether it's looking at systems and crystals or whatever, the choice of what happens here may be different, but that's what's going to fix the problem. Okay? So I'm going to now try to fix this problem using this sort of influence from our program, which is try to put this chiral mode in a crystal. How do I get this in the lattice system? Right? So a crystal to me is anything that has discrete translation symmetry. Right? So empty space has continuous translation symmetry. I can translate by any small amount and large amount I want. In crystals, the defining feature is the fact that I have a discrete translation symmetry. I can only translate by discrete jumps, and that's what I mean when I say a crystal. So what you run into in a crystal, which we're now going to prove, is what's called the chiral doubling theorem. Okay? And this chiral doubling theorem was written down or proven for the first time by Nielsen and Ninomiya in this reference 1 in 1981. They were looking for a way to model the weak interactions in the lattice. The weak interactions has a putative chiral object, which is the neutrino, and they wanted to model this in a lattice system and solve these problems on the computer or look at lattice, standard model on the lattice. So what we're going to do now is we're going to have the first appearance of a crystal, which is just something with some discrete transition symmetry. So I'm drawing these little circles. These little circles represent some type of localized mode. Could be an atomic orbital, like in a tight binding model. It could be a bit of, it could be an LC circuit resonator. So these could be resonance modes in some circuit resonator. It could be a piece of glass where I burned holes in it so that now there's a difference in index of refraction. It could trap a little photonic mode. So these type of things could be anything. But I'm going to think about these in my context sort of being like little atomic orbitals. And so I've got some state n plus 1, n plus 2 on every site. These are my little states, my little resonance modes. There's some lattice constant, A. And I'm going to think about some coupling between the modes, given by some coupling, which I'm going to call T, and there's some phase factor I, which I'm going to attach to in this case. So there's some coupling forward with IT and some coupling back with the complex conjugate minus IT. And this coupling is independent of where I am in the lattice. So I'm going to think about this type of system in this case. Right? So I can write down the dynamical matrix which describes this coupled mode theory If this was in a solid system, this would be the Hamiltonian, a type binding Hamiltonian. We'd have a sum over all lattice sites. And you have terms like I, and you have something like n plus 1 n, so it, and then minus it in n plus 1, where I've used this giraffe bracket notation to represent a transmission between site n and site n plus 1. This thing destroys something on site n and then creates it on site n plus 1. It represents this sort of minimal dynamical process. This system, because it has translation symmetry, the eigenstates of this matrix are plane waves. And so I can write down a solution eigenstate of this thing, which I'm going to label by some wave vector k, which is 1 over the square number of sites, and then sum over sites e to the I k n times the lattice constant n. So this type of plane wave solution diagonalizes this matrix. And when I diagonalize the matrix, we get a dispersion relation, which depends on k. So we get something like the energy depends on k, and it looks like it e to the minus ika minus it e to the ika. And if I write these complex exponentials in terms of sines and cosines, I get 2t times the sine of ka as my dispersion relation. So I want to know two things about this dispersion relation. The first thing is it's bounded, right? It's the energy now, it has to be less than 2t and greater than minus 2t. The second thing is that in the long wavelength limit, right, when k times the lattice constant approaches 0, this dispersion relation is now proportional to k, which is what we wanted in this case. This is why we wrote down this model, so that at long wavelength we get something which looks chiral. Okay. But now if I plot the energy as a function of k, right, we get sine of k. So like this. And indeed, near k equals 0, we get this right-moving shadow. Okay. Now, this problem has an ambiguity, or a redundancy in this case, which is that the energy spectrum is periodic, right? So when k goes to k plus 2 pi over a, the energy spectrum repeats. But furthermore, the eigenstate is the same. If I take k and shift it by 2 pi over a, because n is an integer, that wave function is the same. So I've actually overcounted my solutions in this case, right? And so in fact, what I need to do is I need to restrict k to be in some interval of size 2 pi over a, so I'm going to pick this interval. And this interval is called the Berlin zone. So I'm going to pick, for example, to cut off my spectra at these 2 points in this case. This is pi over a. This is minus pi over a. And now the problem is that at every energy, I hit not only a state going to the right, but I hit a state going to the left. And so at every energy, the net chirality, the sum of the number of right movers and left movers of that energy, is 0. So this model does not have any type of chirality, even though we try to create that at the origin. Okay? And this is a fundamental problem because whenever you have a function that has to be periodic, right, I want to try to create something chiral. It's just not compatible with the periodic Berlin zone. And this is the proof of the Nielsen-Miyanogo theorem in 1D. Right? This is what they showed, and they had a series of 2 papers. They had a simple proof, which is basically along these lines, for this thing in 1D. Okay? So what goes up must come down if it's periodic, and it can't come down in this case. Right? So this is the fundamental problem of trying to get chirality in a discrete lattice system. Right? So now I'm going to talk about ways to violate the theorem to get chirality in a lattice model. I'm going to talk about 3 different ways to do that. I'm going to talk about breaking 3 different implicit assumptions of the theorem to get 3 different physical phenomena in a lattice system, which all have a type of chirality. And after that, I'm going to move on to talk about a new type of chirality in 2 dimensions, 2 spatial dimensions, which is not allowed if you have rotation invariance. And we're going to move on to discuss that if we have time. Okay, so now I'm going to talk about 3 ways to violate the theorem. And I could talk all day about any one of these 3 things. I'm going to try to be brief with each one of them, so you can forgive me for that. So I now want to talk about violating. Right. And my violation is going to be I'm going to avoid the assumptions of the theorem, essentially is what I mean by violating. Right? So there's 3 different implicit assumptions that I care about on that type of dynamical matrix One is that the matrix is local, which means that the couplings decay as some function of distance. In this case, they're truncated. They don't have nearest neighbor couplings. Right? The second thing is that it's time independent. And the third is that the dynamical matrix is Hermitian, so that the evolution conserves probability and you get unitary evolution if this is a quantum system in this case. Right? So I'm going to first talk about breaking locality. And I have a special interpretation of what this means. We can talk about other ways to break locality, but I'm going to talk about one particular way. So let's think about this system. I make a wire of this periodic crystalline system. There's my wire. And it's not chiral. So I have states going both directions. Like that, and like that. Okay. At low energy, this looks like I have a mode going to the right, and a mode going to the left. And I can now couple them, right? I can couple them with any type of perturbation, and then I'll get something which is gapped. So I can open a gap if I now couple them, make an anti-crossing with that crossing point in this case. Right? So what I want to do now is to make a second wire, and a third wire, and so forth. And now each one of these wires has these modes. So these are all just one-dimensional crystalline wires. And now, instead of coupling the things inside the same wire, I want to take this left mover here and couple it with the right mover in the neighboring wire. So I'm going to couple that to gap them out. And I'm going to couple these ones to gap them out. And I'm going to couple these, gap them out. So these parts here all have an energy gap. On the top now, it looks very near the top edge, like I have some chirality, chi equals +1. And on the bottom, it looks like I have some chirality, chi equals -1. So through this procedure, this construction, I have spatially separated the two modes far away from each other in principle. I can separate them arbitrarily far away by inserting more and more wires in this case. What I have sacrificed from doing this is I've had to add an extra dimension. I had to add a second dimension in order to push this one so far away from the other one that it doesn't couple. If I want this mode by itself completely, this has to go to infinity. So I've added an infinite reservoir of wires to couple the system. So this Hamiltonian now, according to the 1D system, is now non-local in 1D because I've inserted an effective extra dimension in this case. Okay. So this type of mechanism is very general. This system now looks like a two-dimensional system where the boundaries have these modes, right? So I have these modes in the boundary. Okay. And this is a model for what's called a churn insulator. It's a two-dimensional system with a quantized Hall effect. And it is a paradigm topological insulator system. So in 2016, the Nobel Prize was awarded for topological insulators to Duncan Haldane, and he produced the first model, not like this, but he produced the first model like this. This type of model was first written down by Charlie Kane and others in reference 2 over there. This type of wire construction model. But essentially, I'm separating the modes by inserting some inert regions in between them in this case.
Right. You have maybe translation and variance in the vertical direction.
So I want to add, yeah, so in this case I'm assuming translation variance in the vertical direction. Right? It's not obvious that on the sides that the modes will come down the side edges, but they do. You can show that the coupling you have to induce, the blue coupling there, actually will have the modes circulate in ways. Anisotropic, but you still get the edge states circulating all around in this case. Okay? So essentially, to get the chiral mode by itself in the lattice model, I have to introduce a whole second dimension. Let's now see how this resolves the anomalous behavior out here, the infinite barrier problem and the charge conservation problem. We can look at that very quickly. So suppose I have an edge of this system here, and I want to put a barrier on the edge. Okay, so I have my mode there. I want to now create some barrier. So I can think about, for example, some barrier like that. Right? I tilt the edge in some way. I cut out part of the edge. It's now vacuum. It's barrier now. Now the mode's just going to go around it. Right? So the fact that it can move in 2 dimensions now doesn't allow it to go through the infinite barrier, but it goes around the infinite barrier in this case. The same is true if I keep extending it downward. Right? If I push the barrier downward further, right, this mode will just go around it. And eventually, if I cut the system apart into 2 chunks, right, this mode will hit the wall, and now instead of going through the infinite barrier, the large barrier, it would just go down the side in this case. So now, because we have an extra dimension in which we can flow, we don't have the infinite barrier problem. Right? The same thing is true of the charge conservation problem. If I imagine now that I have my system on a cylinder, and I want to accelerate the electrons in the x direction, now what happens is on the top edge, I've got my edge state. On the bottom edge, I have my other edge state. When I accelerate the electrons, the top one is gaining charge. The bottom one is losing charge because there's a flow through the bulk in this case, which is the Hall effect in this case. I have some electric field, and there's a Hall effect perpendicular to that field in this case. And so this type of construction gives you a bulk Hall effect and this type of anomalous structure in this case. Okay? So this picture of violating the doubling theorem by adding extra dimension is the sort of foundation for all of topological insulator physics that appears in condensed matter physics. Right? This is a field that was, I would say, originated in high energy physics and lattice gauge theory, because the type binding models we use are exactly the type of models that were used in that theory to model fermions on the boundary of a higher dimensional system. Okay? And there's sort of more generalized and more decorated doubling theorems that you can get when you add extra symmetries, like time versus symmetry and so forth, which represent the different types of topological classes. Okay? So this is one way to violate the doubling theorem to get some type of phenomena, which is this two-dimensional topological insulator physics. The other violations I actually want to stick in directly in one dimension. So here I kind of cheated by going to 2 dimensions. I now want to talk about phenomena that can appear in 1 dimension. So now I want to talk about breaking time independence. So now I want to think about making a system time dependent in a particular way. So I'm going to turn on a periodic drive. So I'm perturbing my system with something with some frequency omega drive, which has some period big T in this case. So I have some one-dimensional system. I'm imagining, for example, shining light or doing some kind of other cyclic perturbation with some frequency omega d in this case. Okay. There's a certain regime of dynamics, which is called flow K dynamics, which is basically a dynamical regime where the periodic stimulus in time gives you a Brillouin zone in energy. So our lattice system has a periodic modulation in space, which gives us a Brillouin zone in momentum. If I have a periodic modulation in time, I can get a periodic Brillouin zone in frequency or energy in this case. Okay? So what that means is that if I have a lattice system which is being driven at some cyclic frequency in the flow K regime, my Brillouin zone is now doubly periodic. It's periodic in energy and in time. So that's something like K, that's something E. I have my spatial Brillouin zone, my sort of momentum Brillouin zone there. Okay. And I now have a frequency Brillouin zone, which has its pi over t, minus pi over t, like that. T. And now the point is that with a doubly periodic Brillouin zone, we can have this chiral channel like this, right? And now this is compatible with a doubly periodic Brillouin zone. Because when I go across in K, now I'm looping also in energy in this case. Okay? So this represents a type of phenomena that can appear in a flow K system where you can have chiral transport that's compatible with a doubly periodic Brillouin zone instead of a singly periodic Brillouin zone in this case. Right? And the physics of this is the physics of what's called the Archimedes screw. So we have this Archimedes the idea, I can imagine some like this. I'll do my best to draw something here. So like this, and I have some. So basically I'm imagining some kind of screw. And I have a handle attached to my screw. I'm going to imagine turning the screw like this, right? And what's going to happen is if I put the bottom in some kind of reservoir, for example, like filled with water or something, right? And what's happening is every time I turn the screw, right, every time I turn the handle, water's going to flow up the screw in this case, right? And so this figure of this Foucault dynamics is that every time I have a cycle driven in this case, I'm pumping something around my system in one particular direction. So for example, I can have the system here, I insert some energy, it sits there, I turn the crank once, it moves in this case. In fact, in this system, it's going to move over, let's say, 1 unit cell every time you turn the crank. This is also reminiscent of something called the Fowlis pump. These things are similar, but not exactly the same phenomena. But the basic picture of the sort of quantized pumping as you crank the cycle is the same in this case. Okay? So I'm going to now talk about the third way to violate the theorem, which is to break hermeticity.
So this sorry, in this old case, in this Foucault system, do you also have this issue of going around the infinite energy barrier?
So this is now in 1D, right? So yes, I mean, in this case, if I have an infinite energy barrier, I don't know what the answer is in that case, yeah? I don't know what the answer is of how to not violate the barrier. I think that problem is much more complicated to solve in this case, right? Because in principle, you'd have to like put in some amount of Foucault energy to go over the barrier, right? Because the reason you can go over any different barriers is because the system has a non-bounded spectrum, so the higher I make it, I just get a higher energy state. And so I think that in that case, you'd probably have some issue, but yeah. Probably it would require infinite Foucault energy going in to go over the barrier, sure. So breaking hermeticity is something maybe that most people here are the least familiar with, right? But this is something which I want to claim is something which is very natural in physical systems. So non-Hermitian dynamical matrices, non-Hermitian Hamiltonians, are models for open systems, like an open quantum system, right? So you can imagine I have some system here, A, in some back, B, okay? You know, if I think about, for example, if I only care about what's happening in system A, then I can find some way to remove the effects of system B. For example, integrating system B out, for example, right? If I integrate system B out, remove its degrees of freedom in some way, I will generate some self-energy for A. And if this has some imaginary part, that's an effective non-hermeticity in the system, right? It's kind of like macroscopic irreversibility, in the sense that I have some system that I care about, I have some large number of degrees of freedom that I don't care about, and I don't track what happens if the energy leaves my system from A to B, right? That adds some kind of effective non-hermeticity to the system. What's interesting and new about non-hermeticity is that now we have ways to control the type of non-hermeticity, because you can engineer different types of gain or loss or dissipation and amplification in metamaterial systems, so photonic crystals, acoustic crystals, circuit resonator arrays. There's ways to control the type of hermeticity so that you can basically control the type of system B you're adding to generate effective types of non-hermeticity in the system that you want in this case. And it's not just decay, you can also have amplification, right? You can imagine systems like lasers, for example, which amplify. So in these non-Hermitian systems, there are models for open quantum system where you can basically engineer the types of dissipation or amplification that you're thinking about, right? So there's a really beautiful idea that actually was originated in this reference number 4, which was by KITP fellow John Lee, which is the following thing. We're going to take our lattice type binding model we already wrote down. So our lattice model, which has the sign of K dispersion. So K, E. I've got my dispersion here. Okay. And what we find is that the velocity here is 0. The modes on this side are traveling in one direction, right? These are all my left movers. And the modes here are all my right movers. So if we could find a way to tune the decay rate of the red states to be different from the green states, right? How fast they decay, how fast they lose, or maybe amplify these states and dissipate these states, right? Then there would be some regime of dynamics where the flow is dominated by the red states, right? So the idea is that we want to turn on gain and loss, or dissipation and more dissipation, in a way that imbalances the red states and the green states, okay? So in that scenario, what we have to imagine we have our wire. I input something here, and because the system's non-chiral, it goes both directions. I get stuff happening to the right, going this way, and I get stuff happening to the left, going the other way. But the stuff going to the left decays much more rapidly than the stuff going to the right. And maybe, in fact, maybe the stuff going to the right even amplifies, so it gets bigger, for example, right? And so I can imagine a scenario where the flow is dominated by this chiral motion in this way. Okay? So there's actually a very simple model which realizes this physics. We can basically change one thing about the model we already wrote down to get this. Right? So we had our model for this crystal. We had our coupling IT and then minus IT, like that. And now in order to get this non-Hermitian structure we want, all we need to do is to tune the magnitudes of these coupling rates to be different in this case. So we have a T right and a T left. This makes the Hamiltonian non-Hermitian. Okay. Furthermore, if we now derive, so this model with this coupling is called the Hitano-Nelson model. It was written down in 1996 by David Nelson and Hitano in the context of vortex dynamics in superconductors, dissipative vortex dynamics. And it was resurrected about 5 or 6 years ago in the metamaterials community, where they began to be able to engineer this type of model in a resonator, coupled resonator system. Okay. So the energy spectrum of this Hitano-Nelson model is just as easy to derive. The plane waves you wrote down are still eigenstates of this model. Right, still translation invariant. And the energy spectrum is given by TL plus TR times sine of Ka. And then we have the second term, which is I, TL minus TR, cosine of Ka. Okay. So this second piece is the non-Hermitian part. It's a complex eigenvalue. If TL equals TR, it goes away. So if it's Hermitian, it goes away, right? And furthermore, this cosine, right, this cosine has one sign in the red region, like that, and has another sign in the green region. And so it exactly imbalances the type of amplification or decay, right? Because the way the wave function is going to amplify or decay, its time evolution is going to be e to the I times this number, and depending on whether this is positive or negative, will tell us whether it decays or amplifies in this case. So this type of imbalance exactly gives us the physics we want and has this Hitano-Nelson model structure. Okay? So this is a way to get anomalous dynamics in a chiral dynamics in a 1D system with non-hermiticity. This model has one other strange feature. So non-Hermitian Hamiltonians are more poorly behaved than Hermitian ones, so the energy spectrum can be complex. Second of all, the eigenstates don't have to be orthogonal or normalizable, and so you don't get completeness. And third, the system actually can be very sensitive to different types of boundary conditions. Usually we don't care if we have large thermodynamic systems whether we use periodic, open, infinite boundary conditions. But it turns out this system has a very strange sensitivity to boundary conditions. And we can see that in a very obvious way. So suppose I cut this 1D wire, like this, for example, this 1D wire. Then I can imagine, for example, let me tune it to be extremely non-Hermitian in this case. We can see now that if I put stuff in here, it has no hope but just to go to the right. That's the only coupling we can get in this case. And so it turns out what happens is that that's perfectly fine if you have periodic boundary conditions, things will just circulate. But as soon as you have open boundary conditions, what happens is stuff begins to pile up on the boundary. And in this system, if you solve the Hamiltonian with open boundaries, you get something called the non-Hermitian skin effect. And this effect is quite strange because on the boundary, it turns out there are an extensive number of modes that live on the boundary. That means there's a number of modes proportional to the length of the chain, right? That's not allowed if you have orthogonality and completeness, because this boundary state, if it's just one mode, for example, can only hold one electron or one object. But in this case, if you have non-completeness structure, you get a buildup of modes in the boundary, which is this non-Hermitian skin effect that people are hoping to use for different types of applications. So furthermore, this non-Hermitian skin effect has been measured in reference number 6, which was a measurement where they built a circuit resonator array, where they built a bunch of LC circuits representing these different dots here. And the couplings represent some kind of circuit elements which can give you some effective non-Hermitian structures. They measure the skin effect, and you can see that. Okay, so this type of physics I've been describing is what I would call physics, chiral physics in spite of being in a crystal. Now I want to talk about chiral physics which can only appear because we're in a crystal. And I want to do this by thinking about how we might extend these pictures to higher dimensions. Everything we've talked about so far is 1D. I want to now think about higher dimensions. So what are chiral modes in higher dimensions, right? In one space and one time dimension, so 1 plus 1D, we have what we've already been discussing. The energy has this dispersion relation. The chirality is the sign of this velocity v. The sort of chiral modes originate in the high energy physics context. And so if you look in high energy textbooks, you'll see that the next dimension you have within chiral is in 3+1 dimensions. And in fact, in order to get chirality here in a rotationally invariant wave, you have to introduce an extra degree of freedom. And so here, instead of having some single band energy, you've got a dynamical matrix, h bar v, momentum, dotted into some two-dimensional space in this case, which could be spin. This could be the Pauli matrices for spin. It could be orbital. It could be any 2 degrees of freedom you want in this case. But we have some Hamiltonian like this, right? And the chirality here is slightly more subtle. Here we have a coupling between momentum, A, and the Pauli matrix. And there's some matrix MAV here. There's 3 momenta in 3 dimensions and 3 Pauli matrices, and so the chirality is just the sign of the determinant. So chi3 is the sign of the determinant of that matrix. In this case, the matrix I chose is the Kronecker delta, just gives us a dot product, and it's a plus, 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 and so the chirality is +1 if this coefficient up here is plus. What about 2+1d? So in 2+1d, there's no notion of chiral objects coming from high energy physics, so we have to do something different there if we want something there. Okay? Let's see how both of these fail to work in 2+1d before we try to do something different. So why don't we get, why can't we use either of these methods to get chiral things in 2+1d? So first, let's take a hint from 1+1. Let's try to create something which has this sort of linear dispersion. Okay? Well, if I create something in 1+1d which has some kind of linear dispersion, right, it goes to the right. But eventually I'm in 2 dimensions, and so I can sort of slowly imagine continuously forward scattering this until it goes the other way. So it can go left now. So there's no disconnected sense in which right is different from left in 2 dimensions, right? Right is also not different from up. I can go right and push it up, right? And so in some sense, this type of thing here does not give me a meaningful way to distinguish the plus and minus sign. So right chirality is the same as left chirality in this case, right? I can have both going to the right and both going to the left, but there's no distinction between the sign. What about the second way? Let's do it with Pauli matrices, right? You have a Hamiltonian and come 2+1d by kx single x plus ky single y, something like that. Okay, why can't that be chiral? Well, from our definition here, like this, right, the problem there is that now in 2 dimensions, my k's are only 2. So now this matrix MAV, right, is now MIA, where I is 2 and A is 3. It's not a square matrix anymore. I can no longer define its chirality. Okay, I can't define its determinant in this case. So there's no natural way to go from 3D to 2D in this way. This is also represented by the fact that there's a third Pauli matrix, and if I add a constant times that third Pauli matrix, it actually destroys the gaplessness of that mode and opens a gap in this case, right? So in fact, this type of object in 2D would be called a Dirac mode, not a chiral mode. It's because it can be gapped in this case by some infinitesimal perturbation. So there's no natural way using this type of rotation invariant structure to go to get a 2+1 dimensional chiral object. Okay? So now instead I want to assume a crystalline environment, right? And by that I'm assuming something which has discrete translation symmetry and possibly only has discrete point group symmetries, discrete rotation symmetries, not continuous rotation symmetry. So now I'm allowed to add different types of dispersion relations, which don't have to have that strong restriction. And so I want to think about a family of things in 1D, 2D, maybe 3D. This is spatial dimensions. So here we have h bar vk. In 2D now, I want to think about this. H bar v times some other number, kx times ky. And in 3D, for example, I might think about h bar v times some number squared, kx, ky, kz. And I'm going to focus for the rest of my talk on this. So this thing here is not rotationally invariant. If I rotate by 45 degrees, it goes to kx squared minus ky squared. If I rotate by 90 degrees, it flips sign. It's not rotationally invariant, right? So furthermore, I want to think about the sign of this thing as being some kind of chirality. But I already have a problem, because as I just mentioned, I can just rotate kx, ky in 2D to minus kx, ky. So I need an extra ingredient, also coming from the crystal. I want to add an extra crystal symmetry. Let's say the mirror symmetry along the line x equals y. This is the symmetry that exchanges x and y with no sign. Okay. Why do I want to do this? Well, if I look at the crystal representations, what this does is this puts kx, ky and kx squared minus ky squared in different representations. And if I want to go from plus to minus continuously, I have to go through that one, right? This is 90-degree rotation. This is 45-degree rotation. if I don't allow this to go here, I can never connect plus and minus continuously in this case. And so I found a way to now discretize or distinguish the two signs. Okay? So I want to now talk about the fact that this type of thing, which is just a saddle point dispersion, has some anomalous structure that was overlooked, or at least was not highlighted, similar to what we talked about with the charge non-conservation. And then we're going to ask, does this type of thing have a doubling theorem of its own or not? And we're going to see something unusual compared to what we saw in the other case. Okay, so I'm going to talk about this, what I'm going to call anomaly, which is just this idea of some kind of non-conserved charge in the system. I want to think about this dispersion relation as a family of modes plotted along the kx direction. So I'm going to imagine now is I pick a value of ky. Let's say pick ky greater than 0. Let's assume the plus sign, pick ky greater than 0. When I do that and plot it versus kx, I get a right-moving mode. Then I pick a different ky greater than 0. I get a different right-moving mode with a different slope. Okay. Now I can pick ky less than 0. Now what's going to happen is the mode's going the other way. So we can see that the sort of total one-dimensional chirality is going to be 0, because that as many modes going right as they do going left. Right? Let's assume now that the system is filled up to some chemical potential. Let's think about electrons, for example. IV is filled up, all the states below this blue line are occupied, and the ones above are empty. And I'm going to write this here. These are here all have ky greater than 0, and the ones over here have ky less than 0. Now if I try to accelerate the electrons by applying electric field in the x direction, right, k then is going to get shifted. And when that happens, the modes in red are going to get an extra mode for every red branch. An extra charge since it's not red branch. But now I'm going to have missing modes for all the green branches. So the total charge is conserved. So when I apply electric field, I don't see an anomaly with electric charge. What we do see is, in this case, is that I added states with ky greater than 0, and I took away states with ky less than 0. And so the electric field in the x direction gives you an anomaly in the y momentum in this case. So this is different than what we saw before, where in another case it was I turn electric field in the x direction, I see an anomaly or a charge difference in the charge, electric charge. Now this is a mixed anomaly between the electric field and the momentum. Okay. If I had some field, right, if I had some electric field that distinguished positive and negative ky. Suppose I had some electric field that was positive for ky positive, and so these increased, but was negative for ky negative. If I had a field like that, right, that would then make both these go up. Okay? So if I had some field in the x direction, ex, which coupled to the y momentum in this way, this could give me a change in charge. This is the inverse effect, where I have a gauge field or field which couples to momentum and gives me something which changes the charge in this case. Okay. This field, although it seems exotic, is not exotic. This is what strain does in the crystal. Right? Strain is a displacement field. Right? If I integrate a strain configuration around the loop, I get a dislocation, which is a translation operator. And so translation operators in quantum mechanics, right, couple to momenta, right, usually p dot d. And so the field that couples to momentum is a strain field. So this is an anomaly between the electromagnetic field and the strain field in this case. Okay? So this is not particularly unexpected in the system because this is just a symptom of the fact that the equipotential contours, the Fermi surfaces of this dispersion relation are not closed. Right? I have a hyperbola structure, right? So I have kx, ky. If I pick some chemical potential greater than 0, my kx-ky dispersion has equipotential contours which are not closed by hyperbolas. Anytime you have a non-closed Fermi surface, you have this mixed charge momentum anomaly. Okay? So I want to ask now, is there a doubling theorem? Is there a doubling theorem for this thing? And this is where the unusual piece goes. So this dispersion relation, this saddle point, is not unusual. In 1953, Van Hove showed that these type of dispersion relations are ubiquitous in lattice dispersions. Right? They're called Van Hove singularities. That's what they are. They appear everywhere. Right? And the way you prove this is using what's called Morse theory. You think about the dispersion relation in 2 dimensions, for example, as a function of these 2 variables. And these 2 variables are actually parameterizing the Brillouin zone, which in 2 dimensions is a torus. This is like a height function, some scalar function defined on the torus. And what Van Hove will show, what Morse has showed, and what Van Hove uses, is the fact that there's a sum rule, which says that the number of minima plus the number of maxima has to equal the number of saddle points. And you can see this is a minimum, this is a maximum, and there's 2 saddle points, 1, 2. And so in fact, in this simple case, you get 1 plus 1 equals 2, so it looks like there has to be 2 saddle points. So this is reminiscent of a doubling theorem. But it's not quite right, because the idea is that it is true, the minimum number of saddle points is 2. Not 1, but 2. But I can also think about a representation of this dispersion relation on the torus, which does this. Now what I've done is I've added an extra minima and an extra saddle point. And so in fact what you can get then is you can get 1 plus 1 plus 1 equals 3. And so in fact there isn't a doubling theorem, but I can't get a saddle point by itself. A saddle point by itself is anomalous, but I can have a system which has an odd number. Right? This is very unusual. And it comes from the fact that this system has what's called UV-IR mixing. The fact that the Fermi surface has low energy modes which span out far in the Brillouin zone. It's coming from exactly this type of effect. Right? So the question we can ask now is that, okay, I can get 3 saddle points in a 2-dimensional lattice model. I can't get 1. How can I get 1? Well, now we can try to violate this theorem in the ways we did before. We can put the saddle point on the surface of a 3-dimensional system. We could think about adding flow K dynamics to try to get a time-dependent system with a saddle point. Or we can add non-hermeticity to take a model which has 2 saddle points and add gain to one and loss to the other. Okay? So this picture of trying to get a saddle point from so let's talk about 2 of those really briefly. I'm going to take 1 minute on each, and then I'm going to wrap up. So I want to ask now, how do I take a model which gets 1 saddle point in this case? Okay. So what I'd like to do now is take a 3-dimensional system and on the surface of it, get a single saddle point. So you can do this. I'm going to draw a mixed sort of space, Brillouin zone, a momentum, and spatial diagram. I have a system which has surfaces, let's say in the z direction, and I'm parameterizing the plane that kicks by a Brillouin zone. So it turns out the 3-dimensional system, which has a saddle point at the surface, is a type of what's called a Weil semimetal. So it's got band touching points, let's say in the Brillouin zone. And for the saddle point, it turns out these band touching points form a quadrupole moment in the Brillouin zone. And when you project to the surface, they give you this saddle point structure on the surface in this case. So there's a particular type of time reversal invariance, inversion breaking Weil semimetal, which has this type of saddle point on the surface. This type of Weil, it turns out that the quadrupole moment of those Weil nodes, defined to be the sum over all the nodes, their chirality, times their momentum locations, Ka, Kb, this sort of momentum space chiral-weighted quadrupole, turns out to control a topological response action in the bulk, which cancels this surface anomaly. You get a mixed strain electromagnetic response in the bulk. It does something interesting, and what it does is it causes momentum to flow in a way that perfectly matches the anomaly you have for that saddle point in the surface. Okay? So you can also think about a way to get this type of saddle point using something non-Hermitian. So for example, you can take a perfectly periodic dispersion relation like sine of kx, sine of ky, 2-dimensional dispersion relation. At low energy, this has a saddle point dispersion, kx times ky. And the Brillouin zone looks like this. It's actually a diamond. And in this system, you get a saddle point at the origin of the Brillouin zone, and you get a saddle point at the corner. And all 4 corners are the same, and so you have 2 saddle points. So now what you can imagine doing is adding gain to this saddle point, and or making this thing dissipate slower than the ones in the corner in this case. And if you do this, it turns out you get a momentum resolved skin effect. So if you inject something with kx momentum, positive kx momentum, it flows to the y surface and vice versa. So you get sort of a momentum resolved chiral dynamics in this case, where you get this object carrying around. Okay? So I said everything in this case about how to think about the chirality. Right? I haven't said why is this thing chiral. I've talked about a different distinction of the sign. So the last thing I'll say is that this type of chirality, I'm going to call it a 2D vector charge chirality. And the idea is that in 2 dimensions, I don't know what front and back is. I don't know forward and backward, left and right. I don't have a sense of chirality. But if my particle, my object, if it carries around some fixed vector, Now what I can do is I can define a chirality with respect to that vector. I can define a right and left with respect to that vector in this case. Okay. And for this particular saddle point, the thing that the fixed vector is being carried around is actually its momentum. So in this case, you get a chirality transverse to the momentum it's carrying, right? Which is why the dispersion is kx times ky. If an object carries ky momentum, right, its dispersion is like kx. So it's like an object which is chiral based upon which direction that vector is in this case, right? Now this is the case when this vector is momentum. You can also pick some internal degree of freedom, like spin or something else, to be that vector charge in this case. But it needs to be something conserved in order to have a well-defined chirality. Okay, let me stop there and I'll take any questions that people have.
Question?
So I guess in 1D, if you want to realize chiral mode, another way we can do it is to break the periodicity of the spectrum by allowing like algebraically decaying whole thing.
Yeah, right. So one thing you can do, right? Yeah. So we can. So if I was an engineer, right, and if I saw like a periodic spectrum like this, right, I would think, oh, that's a sawtooth wave, right? And now what I can do, right, is I can work backwards to tell me how to, so if I want to get the sawtooth wave, right, what I want to do is to work backward to get the Hamiltonian couplings. That's the harmonics of the sawtooth wave, right? For harmonics of the sawtooth wave, right, I have some hopping term like this, and there's a Tj here. The harmonics, which you can know as Tj's, are power law decaying, right? 1 over j. And so indeed, you could generate something like this with a power law decaying coupling. The problem is that in any finite order, this sawtooth rings, right, and drops to 0. And so you don't actually get something exactly chiral. It's canceled by something happening at the Brownian boundary. But in principle, for infinite-sized systems, algebraic decaying could give you some distorted spectrum, which is kind of
So I'm from the other workshop. What we do, I don't know if you are aware, but what we do is we work with nanoparticles as building blocks, and we study all sorts of things from their assembly to the electronic properties and everything. And one thing that I see here, which is that you have these systems that you put in periodic structures, and these systems can be pretty much anything. Yeah.
Yes.
So the question is, can you realize this system with nanoparticles?
Sure, absolutely, yeah.
And has it been done?
So been done? I don't know. I don't think so.
I don't think
People in the engineering field that make lattice systems for sound, for light, for electric current, they're working very hard in these directions because they have real-world applications they want to use for these one-way channels. But I think in the intermediate scale, which is not like I said, these nanoparticles in a sense, I don't know if anybody's working to engineer these type of wave phenomena there. Right?
what
It'd
do
be
you
very
mean
interesting to see.
intermediate scale? What is
I mean, like single atom versus like I have an LC circuit resonator. By intermediate scale, I mean like the nanocrystal system.
an LC circuit resonator that has been done in the nanoparticle world. Because people can do nanoparticles that have the form of like a horseshoe, which has a magnetic resonance, and you can also organize them so that you have oscillator.
Yeah.
And so that can be realized.
Yeah. So I think I was purposely agnostic about how I was getting these dispersion relations. It's perfectly possible that these type of things, everything I talked about here today, it's perfectly possible that almost everything could be realized in that platform. And it would be interesting to consider how to do that, how to design that and engineer that, and what systems might be natural to see there.
Leo?
So the original definition of chirality or chiral systems doesn't mention dynamics. It's really systems that are not superimposable in a mirror image. Like go back to Pasteur. And so I'm wondering what's the connection? Does one imply the other? If you now think about dynamics of, let's say, cholesterics, it implies asymmetry in the dispersion of the left and right movement.
Right. So I was purposely narrow my definition of chirality here to talk about these particular dispersion relations. There's a lot of, I would say, subtlety or semantics issues about whether or not we should call things which are inversion mirror breaking versus time reversal breaking, right? So I think there's some subtlety about that, and I don't want to say anything too clear there. But yeah, I think that, in order everything I'm talking about here requires some form of time reversal breaking. The 1D stuff does. The 2D case doesn't, but the 1D case does. For example, the non-hermeticities like macroscopic irreversibility, I have cases where I'm driving the systems on a broken time reversal, and if I have two-dimensional Hall state that breaks time reversal. So everything in 1D here with that type of chiral channel require time reversal breaking, not just mirror breaking.
Thank you.
Is there a specific model example for this last skin effect in momentum space that you just talked about?
Yes. So there's you can write down any type of two-dimensional type binding model will have saddle points, and you can add a particular type of non-hermeticity. So we actually did this, and I collaborated with experimentalists in the paper I didn't write down there last year to sort of realize this type of non-dimensional skin effect in two-dimensional circuit resonator array.
And it doesn't depend on boundary conditions, because in real space version, you need, of course, open boundary conditions.
So yes, I mean, to see the skin effect, it depends on what your boundary conditions are in this case. So basically, if you just cut the system and have open boundary conditions, you'll get momentum resolved skin effects. If you have periodic boundary conditions, you might get in one direction, you might get a skin effect in this way, but not in the periodic direction. If you have doubly periodic boundary conditions, you don't see any skin effect. And so the system has some kind of hierarchy of boundary conditions, which you can see some effects like that. I'm happy to show you some paper which talks about some of these things. There's still lots of open questions there, but some of this initial stuff has been thought about.
Mark? So what about sensitivity to noise? So all your 1D systems are going to disorder.
Yeah, so the reason that people want to think about the systems, are because they're in principle robust to spatial disorder. Time disorder is noise in that case. Usually those things will still be pretty robust because it doesn't necessarily. For example, the edge states of a quantum Hall system, which are chiral, don't care about too much about coherence in that sense, right? Because they're going in and out of leads, they're losing coherence in leads anyways. They still have this robust chiral property. If I have modes which are going both directions, then I think it's much more sensitive to things like noise because then things can interact in some more complicated way, and you can get sort of decoherence effects which might more strongly affect it. I don't know a better answer to your question, but yeah, certainly these things are super robust to spatial disorder and to decoherence and things like that. It depends, I think, on more details about how many modes there are and those modes go in both directions.
Just a question, maybe / comment about this quadrupole movement of biopoint. So far, I think you have established that the crystalline symmetry is very important to describe to detect any of these chirality. So I was wondering, for example, if I consider 6-fold rotational symmetry systems, and then you can have like a quadrupole, planar quadrupole of biopoints, then it would be tempting to, so template maybe the response would be proportional to the quadrupole moment of the biopoint.
But in that case, I mean, so if you have, with C6 symmetry, I think you will get something which is octopolar, right?
Right.
So there will be a response that is octopolar.
Right.
Just like with anything which is multipolar, in order for the octopolar thing to be well defined, the lower moments must vanish identically. Otherwise, this sum depends on where I choose the origin of my building.
Right. So I can have a plus minus, like 6-fold F-wave like arrangement of the biopoints.
That's right. So in particular, this type of response, which is quadrupolar, requires the dipole moment of the biopoints to vanish, which is the anomalous Hall coefficient.
Right.
And so time resistant does that for me because this is a time resistant variant.
Right.
But there is a way to think about higher moments and what the responses might be. They're kind of more and more baroque in some sense.
Right. But would you expect the response will be also high order, more nonlinear than the quadruple case?
If there's 3 momenta here, then what enters the effective action in 3 + 1 will have 3 different strain fields in this case.
I see.
The issue with having too many strain fields is that while I know how to apply a strain, the charge it couples to is crystal momentum. I don't know how to measure the crystal momentum. So the reason why this is maybe slightly more compelling is that it's a mixed thing between electromagnetic field and strain field. So I can apply a strain and measure a charge or a current, or apply a current and measure something else.
But on the surface for the quadruple case, would you probably have some positive momentum on top surface and negative momentum on the neck?
You certainly would have something like that, but the question is then how to measure that extra momentum.
Right.
Because momentum is not considered crystal momentum. You could imagine crystal momentum really tells you what the phase of the wave functions are doing. And in the metamaterial systems, you can measure the phase of a voltage signal, so I can actually see the crystal momentum there. In a solid state system, it's less clear about how to actually extract some clear momentum because there's scatters all over the surface.
Right.
So
in these systems, the higher powering momentum, the more difficult it is to measure?
I think the less obvious it is how to extract a meaningful quantity. I think there's things you could do, but yeah, I think it's hard.
But you're saying you can realize the biosimilar in metamaterials.
Or even in this case, you can realize this thing by itself in the non-Hermitian system. And then you can really, you can inject momentum by injecting a voltage where the phase shift is set, and you can measure momentum by looking at the phase difference between the various sites, which is what the momentum tells you, right? That if you translate, there's a phase difference, and that's what you see in these cases.
All right, thank you.